So to continue our study of subatomic particles, it's important to know how to diagram them in an easy to understand way. So therefore, we're going to start talking about the Bohr model of the atom. So even though this model is technically considered inaccurate, it gives us a concrete way to diagram the protons, neutrons, and electrons of different elements of the periodic table. So the Bohr model of the atom was theorized in 1911 by Niels Bohr. And Niels Bohr theorized that electrons circle the nucleus in orbits that have a set pathway and energy. He also theorized that the energy of the orbit is directly proportional to its size. So for example, the lowest amount of energy is found in the smallest orbit. He also theorized that energy can be absorbed or released when an electron moves from one orbit to another. And this energy is actually a photon, which is a light particle, and depending on how far the electron travels, depends on the color it becomes. So as a recap, a Bohr diagram is a way to visualize how the subatomic particles, those protons, neutrons, and electrons, are organized in an atom. And electrons are organized into electron energy levels. So we are going to plot or diagram these electrons into levels. And it's important to remember that the levels that are closest to the nucleus are going to have the lowest energy. This is because they have the smallest or shortest pathway. Bohr diagrams help us understand and see how valence electrons work. So valence electrons, this is going to be a term we use in this unit and in our chemical bonding unit. After plotting electrons, the electrons that are on the outermost ring determines what the element will bond with to make compounds. These outermost electrons are called valence electrons. So in 1911, when technology wasn't as advanced as it is today, Bohr theorized that there were 8 different energy levels for electrons. And the first level could hold 2 electrons. The second level could also hold 2 electrons. Nope, not 2 electrons. The first level holds 2 electrons. The second level holds 8. The third level held 18 electrons. The fourth level held 32. The fifth level could hold 32. The sixth level could hold 18. The seventh level could hold 8. And then the eighth level could hold 2. So essentially, Bohr thought it was almost like a palindromic-like sequence. But what we're going to use, and this is actually based off of the periodic table, is that the first electron energy level can hold 2 electrons. The second level can hold 8. The third level also holds 8. The fourth level holds 18. The fifth level holds 18. The sixth level can hold 32, and so can the seventh. And the eighth level, actually, or the eighth row of the periodic table, has a lot of unstable elements, so it's unclear as to what their Bohr diagrams would actually look like. As we model our elements or our atoms, and we diagram their electron sequences, it's important to remember that electrons will fill in the level closest to the nucleus first, because the negative electrons are attracted to the positive protons. What we're going to have to keep in mind is this box right here. This is going to be our guiding factor to figure out how to diagram the different types of levels and electrons. So as a reminder, the maximum number of electrons per energy level are 2 electrons in the first level, 8 electrons in the second, and 8 electrons in the third. So after looking at the information for nitrogen based off the periodic table, it's clear that I have an atomic number of 7 because it's the smaller of the two given numbers, and I have an atomic mass or a mass number of 14. Remember, we always round to the nearest whole number. Based on my previous knowledge of element math, I know that my atomic number is going to represent my number of protons and my number of electrons. But my number of neutrons is my mass number minus my atomic number, so I have a total of 7 neutrons for nitrogen. And we're going to leave valence electrons until the end. So when I plot my Bohr diagram, I have my nucleus, denoted here as a yellow circle. So I remember that there are 7 protons and then therefore 7 neutrons that live in the nucleus. And this is how I model or diagram the number of protons and neutrons in the nucleus. But I have 7 electrons to deal with. So I'm going to draw 1, 2, 3, 4, 5, 6, 7 dots in order to remember how many electrons I have and how many I have left. So according to my cheat sheet, there can be a maximum number of 2 electrons in the first energy level. So I have 7 electrons, so I know I'm going to fill up that first energy level. So I have 1, 2. So I'm going to cross out 1, 2 electrons. Well, this first level is full. There's no more seats available, so to speak. But I still have 5 more electrons. So I'm going to have to go to my second level and plot 1, 2, 3, 4, 5 electrons. So 1, 2, 3, 4, 5. So by plotting the remainder of the electrons I had left, I plotted all 7 of my electrons, 2 in the first level, which filled it up, and 5 in the second. So technically there's still room in the second level, but I don't have any more electrons to plot. So because I'm done plotting my electrons, now I can focus on the number of valence electrons, which remember are the electrons in the outermost ring. So the last ring that I used has these blue dots, these blue electrons, and I have 1, 2, 3, 4, 5. So nitrogen has 5 valence electrons. Let's do another example together. And our second example is with lithium. So according to my periodic table, I have an atomic number of 3, because it's the smaller of the two numbers, and a rounded mass number or atomic mass of 7. According to my previous knowledge of atomic number, that means I have 3 protons and 3 electrons. And to determine the number of neutrons, I have to subtract the mass number and the atomic number. So in lithium, I have 4 neutrons. Because I remember that protons and neutrons are what reside in the nucleus, I can diagram that there are 3 protons and 4 neutrons in my yellow circle, which represent my nucleus of this atom. So now I have to deal with my electrons. And I have 1, 2, 3 electrons, so I'm going to draw 3 dots. And using my cheat sheet, in my first level, I have 1, 2 in the first level, so I cross out 2 of my dots, but I still have 1 left. So that means I have to go to my second level. So after plotting the remaining electron, I'm out of dots to plot. So that means that I can focus on the number of valence electrons, which is the electrons in the outermost ring. So the last ring that I used was in the second level, and I have 1 valence electron. Now a question I want you to ponder is that I only used 1, 2 energy levels for nitrogen, but I also used 2 energy levels for lithium. Looking at the periodic table, what do lithium and nitrogen have in common in terms of their placement? Let's do one more example together before you do helium on your own. We have our fun cheat sheet off to the side, and eventually you'll have this memorized because you'll use it so frequently. The first thing we do for a Bohr diagram as a brief reminder is we always look at our periodic table. So we identify our atomic number, which is 13 for aluminum, because it's the smaller of the two numbers. And then I have 26.98, which will round to 27. Based on your previous knowledge of protons, electrons, and neutrons, my atomic number is going to be 13 protons and also 13 electrons. For my number of neutrons, I'll have 27 minus 13 is equal to 14 neutrons. Remember, I can't do anything with my valence electrons yet because that's how many electrons are on the outermost ring. So let's go to our diagram. In the yellow nucleus, we're going to write down that we have 13 positive protons and 14 neutral neutrons. So that takes care of our mass number, or the mass of the nucleus. So now I can focus on the number of electrons. So because I have 13 electrons, I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 dots to represent my 13 electrons. Looking at my cheat sheet, it says that I can put 2 of those 13 electrons in the first energy level only. So I have 1, 2. So I'm going to cross out 2 of my electrons. I clearly still have more to go, and I have more than 8. In fact, I have 11 left. So because my first level is full, I'll have to go to my second level. But my maximum I can hold is 8 electrons. So I'll put 1, 2, 3, 4, 5, 6, 7, 8. So now I'm going to cross out 1, 2, 3, 4, 5, 6, 7, and 8. So the second level is full because I can only put 8 electrons in the second level. So what this means is that these remaining 3 electrons have to go into the outermost ring available to me on my diagram. And because I've plotted the last 3, I can cross out the last 3 on my cheat sheet. So after I plotted my 13 electrons, 2 in the first level, 8 in the second, and 3 on the third, now I can focus on the number of valence electrons, which are the number of electrons in the outermost shell. And so because I have 1, 2, 3 electrons in the outermost shell, that represents that I have 3 valence electrons. In the previous slide, I asked you to look at where lithium and nitrogen were located in terms of placement on the periodic table. On the periodic table, they're both in the second row, and we only use 2 rings. If you look at aluminum, aluminum is in the third row of the periodic table, and aluminum uses 1, 2, 3 energy levels. So what type of assumption can we make about the number of energy levels versus what row or period the element is located in on the periodic table? This question will be a warm-up question later this week, so it's important that you think about it and determine what type of relationship is there. But now I need you to complete helium on your own, so then when you check in, I know that you've attempted a problem individually.